Hello, calculus students. This is section 5.5. We are now going into triple integrals, but not just triple integrals. It's triple integrals in cylindrical coordinates and spherical coordinates. Let me just give you one little quick thing. Triple integrals in the cylindrical coordinates, easy, no problem, okay? Spherical, not so easy, right? But it's really not impossible. And I have what I have done is I have created an extra part of this video for an optional understanding of what that dv is. You have to have dv, which is like dz, dy, dx in rectangular coordinate system. And it turns out to be pretty easy in cylindrical, but not so easy in spherical coordinate system. But I have explained why dv is such a long expression in spherical coordinates in a separate part of this video, all right? And so in the main part, we will just assume you know what the dv is. All right, so with that, let's get started. All right, so this is section 5.5, all right? So triple integrals in spherical and cylindrical coordinate systems. All right, so let's do a little review. Okay, we're not going to spend a lot of time on this, right? But you know that we have a rectangular coordinate system where you have x, y, and then of course you can draw a line here like this here, right? This is your z, and we can think of this point as x, y, z, right? And this is a rectangular coordinate system. Or you can think of this, and this you can call this r, and this is theta. And you can call that point P. Let's see, P is XYZ in XYZ or rectangular or Cartesian coordinate system, but P can also be called R theta Z, right? And that is the cylindrical coordinate, right? And so, for instance, in cylindrical, if you talk about equation like r is equal to 2, what is r is equal to 2? What does it look like in a cylindrical coordinate system? Well, it's basically a cylinder, right? A radius 2, and so that means x squared plus y squared is equal to 4. There's no reference to z because it's a vertical cylinder, right? So that's how you would write this in the Cartesian coordinate system, but in cylindrical, it's much easier. R is equal to 2, right? What is z is equal to r squared? Well, that would be x squared plus y squared in rectangular coordinate system. And I hope you will see that this is a circular paraboloid like this, right? Where this is, z is equal to r squared. Okay. If z is equal to r, then what we are saying is z and this length r is the same, and so you could expect a cone, and that is exactly what you will see. It's a 45-degree cone like this, and you will see that. And actually, assuming, well, let's see. Sometimes you allow r to be negative, and sometimes not. I mean, if r is assumed can be negative, I guess you can make this in the other direction as well. Okay, so let's go ahead and try to just jump right into a triple integral, right? So I am going to draw a picture, okay, of a quarter of a cylinder. So it'll look something like this. Imagine like maybe a piece of cheese or something, okay? And let's say here, this is 4 and this is 4. So x 4, y is equal to 4. So maybe I should say 4, 0, 0. And this is 0, 4, 0. And let's say z is equal to 3. So the height of this piece of cheese is 3. Okay, so this is 4, 0, 3, and this is 0, 0, 3. Okay, how big is this? What's the volume of this? Well, you don't have to know calculus to know the answer, right? The volume of this turns out to be, well, let's see, it's 1/4 of pi r squared, and r is, of course, radius is 4, right? The radius is 4. And so it's 4 squared, and then, of course, you multiply this by height, which is 3. And for, I mean, this is 16, but you divide it by 4. It's 4 times 3 times pi, and it's 12 pi. No problem here, right? Okay, yeah, but we're supposed to be doing calculus, so why not use calculus? Yeah, we can. And so here's the way we think about this. In cylindrical coordinate system, by the way, what in polar, we already saw that dA turns out to be not the r, the theta, but there's something that comes in front of it, right? And then I explained that is r. Right, so in cylindrical, we pretty much use that along with z, because z just goes straight up, right? So it's dv is equal to, right? And you have r, but then you still have dz, dr, d theta. Okay, so this is what we will be using, not hard. Okay, so like for instance, over here for this problem, you notice here theta goes from what to what? All right, that's from 0 to pi over 2. That's 90 degrees. Okay, that's 1/4 of an entire circle, right? R goes from 0 to 4. Okay, see that? Here's 0, and then it goes all the way to 4. And it goes in all directions as theta ranges from 0 to pi over 2. And then Z goes from 0 to 3 at every point of this. So if you pick an R and theta, you have this point here. Actually, if maybe I should be talking like what we did in triple integrals in rectangular coordinate system. When I write this, what I mean by that is, I'm doing this from the outside and then going inside. I'm working my way from outside in, right? And so theta is from 0 to pi over 2. And if you cut this this object, whatever it is, I'm not cutting the cheese. All right, so if you cut this at a certain theta, an angle, okay, let's say here, the slice or the cross section is going to be this rectangular piece. Okay, actually maybe it's a sliver, something like this. All right, and then if you pick a particular r, let's say r here, then that will give you z from 0 to 3, right? And of course, the z value is independent. The range of z is independent of the theta or the r that you picked. And so that's why this is really simple, okay? And so here's the first triple integral in cylindrical coordinate, right? Coordinates. The volume turns out to be, okay, can you figure out? From 0 to pi over 2, from 0 to 4, from 0 to 3 of r dr d, sorry, r d z dr d theta. Now it's possible to switch the order of these, but in cylindrical coordinates you hardly ever see any other order except dz, dr, d theta, and typically you do not have to switch things around. All right, so this is going to be a very simple exercise. You have r and then z going from 0 to 3. Of course, that's just 3. And so let's take that out. You have 3, and then 0 to pi over 2, 0 to 4, and then you have r dr d theta. And so this is 3, 0 to pi over 2. And then you have r squared over 2, which is a very common thing for you to see when you evaluate triple integrals in cylindrical coordinates. All right, so that's 8, right? So it's 3. And then 16 divided by 2, that's 8. And then, of course, you just have pi over 2 at the end. So this is 3, 8, pi over 2. And you can tell this is 12 pi, as we expected. All right, so really, there's not much that you need to do for a cylindrical coordinate system. All right, sometimes this z, of course, depends on, your choice of r and theta. So let's look at the volume next of a sphere. Okay, how about the sphere of radius? I'm not going to fix the radius, just the radius a. Okay, so you have this sphere of radius a. Let's draw that. Okay, so that's what the sphere looks like. So nice to have this of this thing, right? Okay, so and to make it look, three-dimensional, you just kind of draw an equator, and somehow our eyes start to see a three-dimensional, object as opposed to just a flat circle. And so I am saying for this particular problem, let's say the radius is A, okay? Now, you know the answer to this because you memorized the formula, right? So the volume, oh, that's not what I want to do here. You know the volume from the formula. All right, so the volume of the radius R sphere is 4/3 pi times R cubed, right? So now we just replace this with A. So that is the answer to this question. How did you know this, by the way? Is that because your geometry teacher told you that? You just believed everything your geometry teacher taught you? Well, how old is this thing? I mean, did somebody work this out with calculus? And yes, we are about to figure out this formula, derive this formula using calculus. But the story of this formula goes way back, like 2,500 years ago, okay? Who in the world would figure out the volume of a sphere 2,500 years ago? Well, the answer is, of course, the Greeks, right? And in particular, Archimedes, through very, very innovative thinking, figured out the volume, which is 4/3 times pi R cubed. And that was based on his other well-known formula, which is the surface area of the sphere, which is 4 pi R square. How in the world did they do that? Well, the Greeks were the amazing, incredible people. Okay, so we are about to find this using and later we will do this using spherical coordinate system, which is much easier. But for this, we will just use what we have, which is so far cylindrical coordinate system. Okay, so here is the way you would think about this. All right, you pick, right, so here the volume is, well, let's see, what is that? Theta goes from 0 to 2 pi, of course, because we were talking about the entire sphere, right? And how about, R, okay? Well, R, well, that's easy. That goes from 0 to A at every angle theta. Okay, so that's not too bad either. But what's one problem is once you pick a point, which is on a particular theta and a particular R, then you go from this point to this. Actually, you go from this to this, right? But let's just do let's go from here to here, right? How do you describe this? Well, the sphere is x squared plus y squared plus z squared is equal to a squared, right? Of course, you don't want to use x and y, so you can even do this r squared plus z squared is equal to a square, right? So maybe I should not have this here. Okay. So this gives us a clue. Okay, let me go ahead and write this over here too. Right, so give me just a second, and then I will bring this. Okay, so I just rearranged the writing so that it'll be obvious here. All right, so for each point you pick, z goes from what to what. That's what we have to do. And so z, if you solve this for z square and then take the square root, you get plus or minus, because you have the negative and then the positive side. Square root of a square minus r square. Okay, and that is what you would end up writing here at the end. For z, it goes from negative, what's this thing here? Negative a square minus r square, and then to positive square root of a square minus r square. All right, so then your volume is going to be from 0 to 2 pi into triple integral, from 0 to 2 pi, and then from 0 to a, and then from negative a square root of a minus r squared to positive square root of a minus r squared. And then what comes in here? Yeah, the first thing is r, okay? Don't forget that. And then you have dz, dr, d theta. Okay, now that's all right, but it's really annoying to have this thing here, right? So this is where you can use a symmetry, because you know that the upper half is going to look exactly the same as the lower half, right? And it makes the calculations somewhat easier if you just start at 0, okay? And so I am going to rewrite this so that we'll have twice, the volume of the sphere is twice the volume of the upper hemisphere. And so this is what we can do. All right. all right, let's go ahead and do this. This is 2 times the integral. And then, well, let's see, what do we have? See, the first thing we do is to integrate with respect to z, right? So this just becomes the square root of, sorry, it's a square minus r squared, that's all under the radical, right? And then you have r, and then you have dr d theta. Now, of course, you have 0 here, so you don't have to worry about the other part, which is nice. All right, is there a way to continue here? Of course there is, right? All right, so at this point, I am going to let a square minus r squared to be u. Good old u substitution. It's so wonderful. U is so amazing, just the way u is. And so du is negative 2r dr. And when you do that, remember, these things also change, right? So u, all right, so when r is equal to 0, u goes from, let's see what I can do. When, the way this is tricky because you have to kind of keep track of what's u and what's r, right? If r is equal to 0, that means u is equal to a square. If r is equal to a, then you plug in, you know, a square here. So u becomes a square minus a square, which is 0. Okay. All right. So do I have negative 2r here? I don't. Okay. So I can just create a 2 here and minus 2 here, right? So what I'm saying is I wish to see a negative 2r dr because that's what I need. Okay. And so I can just sneak it in there and pretend like I didn't do anything wrong. Or I can just divide both the inside. I mean, I can enter this and then I can divide the outside by negative 2, right? And that is the right thing to do because you don't want to change the answer. Okay, so this becomes negative and then integral from 0 to 2 pi, 0 to, oh no, you can't have 0 to a anymore, right? So what happens here? This becomes a square to 0, and then the rest is, well, it's u to the 1/2, and then this whole thing is du, d theta. All right, so this is what you will end up integrating. Now, you know, I personally dislike having a number here and 0 here. Okay, they should be the opposite. So in my next line, I'm going to get rid of this negative sign and change into a positive. And then switch the order of this. So it's 0 to a square, right? And then a to the 1/2. No, that's a, not u. U to the 1/2, and then du d theta, okay, which is much, well, somewhat easier, I think. All right, and so what do you get? It's u to the 3/2, and then of course you have 2/3, right? And then you plug in 0 and a square here and d theta. So this is, and let's just keep everything inside here. What you have is a cubed, right? Because what you have is a square, and then you take 3/2 of it. So that's you know, a cubed, right? It's a square root of a squared, and then you cube it. So that's a cubed. And then you have d theta. This whole thing is a constant, okay? So this becomes 2/3 a cubed, and then you just have 2 pi, right? So then you have 4 over 3 times pi, and then a cubed. Does it sound right? Does it look familiar? Yeah, that is exactly what Archimedes figured out 2,500 years ago without using calculus, all right? But what happens is calculus actually verifies that Archimedes was a genius. All right, so that's, you know, as expected. This is what you get. All right, I'm going to pose a question, Jeopardy question, and then I will give you time to sing your Jeopardy theme song and then answer your question. And so let me ask you this. The answer, the category is triple integrals. Here is the answer. V is equal to the integral from 0 to 2 pi. Can you imagine Alex Trebek reading this? And then from 0 to 3, and then from 0 to 9 minus r square, r dz, dr, d theta. Okay, you have 30 seconds to figure out what the question is. All right, so when you think you know the answer, and maybe you can go ahead and calculate this, and then you can start the next part of this video lesson.